taking integrals. Now we've done it with a graph. We've actually added up the areas, but there's more than one way to do this. So let's think for a second. Inverses. Inverse of 5. 1/4. Well, I mean, we could do that. The inverse of 5 is -5 if we were talking about additive inverse. Inverse of 1/4 is 4. Think about multiplicative inverses. Inverse of boy, I guess you could say cat. I mean, girl, I'm reading ahead. Cat, maybe dog. But inverse of taco? Inverse of movie? It's really hard to do inverses when we have nouns. So when we think of inverses, it's not just the opposite. Really, it's the opposite process. So we really take inverses of verbs, not nouns. Let's try it again with this table. What's the inverse of standing up? Sit down. What's the inverse of waking up? Going to sleep. Inverse of drying off? Taking a shower. Inverse of getting dressed? Undressing. Inverse of shouting? Whispering. Inverse of eat? I'm not even going to go there. So the inverse process is what we want to think of, you know, like squaring. My video kind of cut out there, sorry. The inverse of squaring is square rooting, cube root, exponentials, logarithms. The inverse of derivatives is antiderivatives. So what would be the antiderivative of 2x? In other words, what function, if I take the derivative of it, do I get 2x back? Can you think of one? A lot of people are going to say that it would be f of x would be x squared because the derivative is 2x. Is that the only function? Well, I can think of some others. What about x squared plus 4? X squared minus 17. Oh my gosh, I can keep going, huh? So it's not that the antiderivative is unique. We have infinite possibilities. There could always be a constant at the end. So we have to take into consideration that there could be some number added or subtracted at the end. So let's look at the processes we can have. So the shorthand symbol for an antiderivative is also the integral. So how could we write the antiderivative of 2x? Well, that would mean we're looking for the integral of 2x dx, which would be, we all know x squared is part of it, but plus some c, some constant at the end. So we're going to use derivatives we already know to fill in the table and then fill in the antiderivative. So sine x, the derivative of sine x is cosine x. That means the antiderivative of cosine x is sine x plus c. The antiderivative of, and the derivative of cosine is negative sine. So if I had negative sine x and I was trying to find the antiderivative, it'd be cosine x plus c. What about tangent? Derivative of tangent is secant squared So if I was given secant squared and I want to know its antiderivative, it'd be tangent. Oh, plus c. What about the following? Now, you've already taken notes on these before. And remember, if you ever forget what these are, cosecant is 1 over sine. You could then use quotient rule. But cosecant is negative cosecant x cotangent x. So if I was ever given that, I know that's cosecant x plus c. Secant, if I forget the rule, it's 1 over cosine, and then I can use the quotient rule after that. But it gives me secant x tangent x. The antiderivative would be secant x plus c. Cotangent gives me negative cosecant squared. So if I was given negative cosecant squared, its antiderivative would be cotangent, and so forth. What about the arc sine or inverse of sine? 1 over square root of 1 minus x squared. So if I was given that, I know that's inverse sine plus c. Cosine would be negative 1 over square root of 1 minus x squared. See if I remember tangent. Inverse tangent, its derivative is 1 over 1 plus x squared. So the antiderivative of that would be tangent, inverse tangent, plus c. The derivative of e to x, my favorite, is e to the x. So the antiderivative of e to the x is e to the x plus c. A to the x would be natural log of a times a to the x. Antiderivative would be a to the x plus c. In derivative natural log, 1 over x. Anytime you have 1 over x and you're taking the antiderivative, that's just natural log of x plus c. Don't forget the plus c. Any other logarithm, it's still 1 over x, but we take the natural log of a, of that base. So if I was given 1 over x and the natural log of a number, that means it's going to be log base that number of x plus c. Now, memorizing all of these is not fun, right? Nobody wants to do it. So we're going to look at some tools, shortcuts that we can use to undo derivatives, kind of the same as when we took derivatives. So, remember that if we took the derivative of a constant, we got 0. So, the antiderivative of 0 is some constant. The derivative of a single variable was just its coefficient, or just 1. So, the antiderivative of 1 would be x plus c, plus some constant. I could have a constant after that. If I multiply a function by a constant, that's the same as the constant times the derivative. So if we have a constant times a function, that's going to be the same as that constant on the outside, and we could take an antiderivative. That's an important rule, too. What about if we were adding and subtracting? Remember, we could split it up. Same thing here. I can split up my integral into the integral of f of x dx plus or minus the integral of gx dx. Now remember, when I actually take the antiderivative, I'm going to put plus c at the end. power rule. The exponent came down, and then we subtracted 1. So what would be the inverse of that? Well, I'd have to add 1 to the exponent and then divide by that new exponent. Example. The antiderivative of x cubed. I'd have to raise it to x to the 4th, but to make sure it came back to be just 1x cubed, I'd have to have 1/4 in front. What about the chain rule? Well, we'd have to see that we have the derivative of some function times that function's derivative to notice that we have the chain rule. If you see that you have the chain rule, you should say, thank you, Lord. F of g of x dx. We're going to look at how to use that because that one is a little bit trickier than some of the others. But let's start with the simpler ones.